I just came to realize when Dr. Bellmeyer and I were talking on Monday, or Friday or whenever it was, that he's really doing a lot of his lecturing out of Hertzberg. Did he tell you that? Okay. But some of his graphs and stuff are out of Hertzberg. I opened this up this morning for about the third time in my life. Okay, it's been around my bookshelf. It's written in 1977. Hertzberg was a deformation and mechanics metallurgist at Lehigh University, and I think actually he was an MIT grad, if I remember. But anyway, yeah, got his MS in metallurgy from MIT and PhD from Lehigh. Hertzberg really is sort of a fracture guy, which to a certain extent, well, I was looking at it this morning, he starts out like chapter 2 is dislocations. Back often uses the word dislocation 3 times in the entire book. Okay, so back often is sort of a continuum mechanics guy who's worried about how do you extrude things, how do you roll things, how do you draw sheet metal. And Hertzberg is a fracture guy, and so if you think about it, Dr. Bellmeyer, who's also a fracture person, likes to worry about dislocations and things. Back often likes to worry about things like clay, Back often worries about crystalline things, but a lot of what he does, it doesn't really matter if it's got crystal structure or not. And then he kind of adds crystal structure on top of it. But back often used to hate dislocations. When I was a student, I took a course that was Introduction to Dislocations. And it was a 800-page book. And I don't know how much people know about dislocations, but dislocations were conceived theoretically about 20 or 30 years before anyone had ever seen them. Okay? People knew that metals deformed at a much lower stress than theoretical stress. Once people started studying quantum mechanics and looking at the strength of bonds around 125 years ago, they started doing calculations just like the nanotube people do today, okay? The nanotube people will tell you that nanotubes have a strength of 3 million psi. And they say, isn't this fantastic, we discovered this new science. Well, people did that calculation 125 years ago. The inherent strength of a primary chemical bond is about 2 or 3 million psi to pull it apart. If you take how many atoms or bonds there would be in 1 square inch, it'd be 3 million psi to pull them all apart at once. But how many metals do we have with 3 million psi strength? Well, we actually do have some. But it wasn't until the 1950s. But so people were trying to understand it, and 2 guys came up with it. One was it Polanyi in Hungary? Anyway, the other one was, Polanyi. Anyway, there's a guy in England. Can't remember if it was Polanyi, but anyway, the other one was Egon Orawan in Hungary. And Egon Orawan ended up in mechanical engineering over here at MIT. He was towards retirement when I came as a freshman, but he was still teaching a couple of courses. He learned about dislocations because he was at some academic institute in Budapest or whatever, and he had this big office and it had a big oriental rug, and the rug was slightly shifted, and the maid was cleaning and stuff, and she says, oh, the rug needs to be moved. He says, well, let me help you because it's a big heavy rug. And she says, no, okay, I can do it. And so she takes the rug, and he just watches her, and here's the rug lying there, and she puts a dislocation in the rug by just putting a little, and she kicks it across the room, okay? And the rug moved about 6 inches. And he looked at it and thought, that's how metals deform. And so he came up with dislocations. And so dislocations, you're breaking one atom at a time, or one row of atoms at a time, rather than a whole plane of atoms. And therefore, he came up with dislocations, and I can't remember who the other guy was. But anyway, somebody in England. They both independently came up with the concept of dislocations in the 1930s. It wasn't until John Gilman in the 1950s looking at lithium bromide or something, some sort of lithium salt, single crystals, did etching experiments, and that you could etch right at the dislocations in the single crystals. And so he had these beautiful pictures. This was before we really had transmission electron microscopes or anything, but he could find these things, and he would deform the crystals and show that he would get a lot more of these pits because he was creating dislocations. Okay? And he proved dislocations by doing this metallography, okay, in the etching process. And then along came the transmission electron microscope, and people could see them and things. So we knew a lot about dislocations. And so in the 1950s, this just became, just like nanomaterials today is the big thing everybody works on. In the 1950s, everybody just started calculating dislocations. And so by the time, 15 years later, when I was a student, there was an 800-page book by Hertz and Wolfe on dislocations. And you'd solve these equations. It just went on for page after page about the Burgers vector and all this stuff. And I took the course and I passed it, and I've never used a thing since out of it, okay? Except I do know what a dislocation is. So far as, did we ever make any material that had that strength? In the 1940s, we made iron whiskers, which had a screw dislocation right up the axis of this whisker. Anybody knows anything about dislocations, if you pull in the same direction as the screw dislocation, then there's no stress on it. A screw dislocation moves by shear through the material. And they pulled these whiskers experimentally. They measured 2 million psi. So now, 40 years later, I hear about people discovering carbon nanotubes with these tremendous strengths, okay? Except the problem is the physicists assume a perfect crystal with no dislocations. And at what temperature is that true? Absolute zero, right? So at any temperature above absolute zero, you're going to have some vacancies in those nanotubes. And guess what's going to happen to the strength of that nanotube when you have a vacancy? I mean, I can rip the piece of paper for you. I've already ripped it, show you what a notch does, right? So there's a guy, yeah.
I'm just curious, if you were to have a number of nanotubes, the vacancies in the tubes would be scattered throughout.
Right.
Couldn't you have a situation where you, I guess...
Statistically, you're thinking?
Yeah.
Statistically, it's going to be weak. I mean, a chain is as strong as its weakest link, right? So if I go to higher temperatures, it becomes weaker with more vacancies. So if I have lots of nanotubes, yes, 10 nanotubes are probably 10 times stronger than 1 nanotube, but that doesn't mean that it'll be 3 million psi, because it's still per unit area. Okay, and if I still have a flaw, there was a guy, what was his name? He was head of materials at GE Aircraft Engines in Cincinnati, and he was quite outspoken about things. He was the guy who, I can't remember his name right now, but he was the one who said, when you first hear about the properties of a new material, write it down. Those are the best properties the material will ever have. Okay, and there's the Jim Williams corollary. Jim Williams was dean at Ohio State and department head at Carnegie Mellon, and is an expert on titanium. He became head of materials at GE Aircraft Engines after, the other guy was Bob Sprague back in the 70s. And Jim Williams in the 90s became head of materials at a GE Aircraft Engine. And Jim had the Williams corollary to Bob Sprague quote about the properties of a new material. He said, whenever you first hear about the cost of a new material, write it down, because that's the lowest cost the material will ever have. Okay? So if the usefulness of a material is somehow some ratio of properties to cost, the properties are always going to decrease and the cost is always going to increase, and so that means that the value of that material from when the first person discovers it, and the thing is going to change the world overnight, right? And it's just going to go diving ever since. So in 1980, was it 88 or 89, they discovered high temperature superconductors. Oh, you could not get a research grant from the National Science Foundation for a year and a half unless it had the word high temperature superconductor in it. Seriously. Every new grant, they basically set a policy because this was going to change the world overnight. I thought it was very telling because at the time there were 5 faculty in this department who had worked, out of about 35, who had worked on superconductivity prior to the discovery of high temperature superconductors. Bob Rose, Harry Gatos, Tom Eager. I did my doctoral thesis with Bob Rose. Can't remember the fourth one right now. And Dave Redmon. And everybody, I mean, within 6 months, everybody, I would say 75% of the people in the department were now working on high temperature superconductors. And the only one of the 5 who had worked on high temperature superconductors before that went into the field was Dave Redmon, because he didn't have tenure. Okay? There's a guy who has tenure in electrical engineering who had been denied tenure in 1988. And when they discovered the high temperature superconductors, a month after he was denied tenure, the electrical engineering department went back and said, oh, we better keep this guy because he knows something about superconductivity. So he got his tenure after being denied tenure, and you could do that. There was like a 2-month window, and this whole discovery occurred in that 2-month window. He's still here, so I won't tell you his name, but he got tenure because someone else got the Nobel Prize, okay? And everybody said, oh, this is going to change the world. Well, you know, whether it's fine ceramics in the 1980s or superconductivity in the late 80s or photonic materials in the 1990s, or whether it's nanotubes around 2000 or biomaterials in 2005, we go through these cycles of this material that's going to change the world. Well, the 4 people who refused to work on high temperature superconductors because they knew superconductivity. And they knew that you don't just live with one parameter alone, okay? High temperature superconductors, they have a high temperature, okay? But you can't make anything useful out of them unless you have a few other properties. Anybody know what the critical properties are? This is figure 1 of my doctoral thesis, by the way, okay? I have this fancy figure that shows 3 dimensions for a superconductor. And this is the phase region down in here. This is the critical temperature. This is the critical magnetic field. And this is the critical current density. Okay? It's not just T sub C that's important. That's what won the Nobel Prize in 1988. Okay? And I could probably figure out some similar plot for nanotubes or buckyballs or whatever. Okay? One property, and everybody said, oh, it's going to change the world. Well, it turns out that there is a good correlation between T sub C and the critical magnetic field. You go above a certain field and you lose your superconductivity. Well, when I was working on these, I was working on some of the highest temperature superconductors, worked at 20 degrees Kelvin, okay? And these things had critical fields. The niobium aluminum had critical fields of, I don't know, 30 Tesla. Anybody know what a Tesla is? Have any feel for a Tesla? The strongest magnet, electromagnet with an iron core is about 1 Tesla. Okay, an Alnico magnet is about 1 Tesla. Iron neodymium boron might be 2 or 3 Tesla. Okay, and the strength of the magnetic field basically goes as the square of the field. Okay, so 30 Tesla is 1,000 times stronger than the magnetic field you have in a regular old motor. Well, you can't use all 20 degrees Kelvin. People were going to operate at 4.2 Kelvin, so they would still have, because at 20 degrees Kelvin, you have 0 field. Okay, B is 0. Okay, pretty useless to make a magnet out of something that's not going to be magnetic, right? Not going to be superconductor. So we're going to operate down here. We had to operate somewhere within this region. Now, so there's a good correlation between these two. But what about this one? The critical current density, it was known, in fact, the superconductors that were being used for the high energy physics experiments in 1970s, okay, were typically niobium titanium. And the guy who really worked here a lot on that, he didn't discover them, was John Wolfe. John Wolfe was teaching 3091. He taught 3091 when he turned 65, and he couldn't teach anymore under the old rules. You had to retire at age 65. Before about 1982, or somewhere in around 1980, Congress with an average age of 77 passed a law that you could not force a faculty member to retire at age 65. But before that, all MIT faculty had to retire at age 65. John Wolfe retired at 65, and they had this thing that you could keep teaching for 5 years until you were 70, but you could only earn half pay. Okay, so John Wolfe, in order to earn half pay, started teaching 3091. John Wolfe had worked on niobium titanium. Niobium titanium had a critical temperature of about 9 degrees. So you were only about double that, and the critical field was like, typical field might be 6 Tesla. Okay, well, that's okay, but it's not great. But then a guy named Mark Benz, who had done his doctoral thesis here in steel making, went to work for General Electric Research, and they came up with niobium 310. This is not what I was going to lecture on today. And niobium 310, they found that if they put zirconium in there, 1% zirconium, they could internally oxidize it and form zirconium oxide precipitates on a nanometer scale. I can use that term today. We didn't call them nanometer, but basically it was like they had to be like 100 nanometers apart. These were like 20 or 30 nanometer precipitates, because that's what gave you a good critical field. If you had really pure stuff, you wouldn't get decent properties. In fact, if you want to know and back off, and I showed you the picture of and I don't know if I can find it quickly, but the wavy slip of the niobium that had been drawn 88%. Back off and got that picture from one of John Wolfe's students back in the 60s, because they were working on severely deformed niobium. My house tutor did his doctoral thesis on severely deformed niobium as a superconductor. I don't think I can find it quickly. But there's a picture in here and I showed you the wavy slip when we talked about asymmetric deformation and two-dimensional stuff. And so that's kind of the historical context of where that comes from. But getting back to the high temperature superconductors, and why 4 out of 5 of us, the 4 of us that had tenure, wouldn't touch high temperature superconductors, is we knew there was a scaling factor between critical temperature and the pinning sites, these little imperfections that keep the magnetic flux lines from just wiping through the crystal and wiping out the superconductivity by just Joule heating. Okay, if the magnetic flux lines are not pinned, there is a force, a J cross B force, the Lorentz-Maxwell equation, Lorentz force, is trying to push the magnetic field flux lines out of the crystal or out of the superconductor. If you have a current going this way, you have a force perpendicular to that trying to push the magnetic field out of the superconductor. And if it's successful, the thing is no longer superconducting. Well, in order to get a good critical current, you had to pin the magnetic field on imperfections. And the size of the imperfection you wanted scaled inversely to the critical temperature. If you take these 40 and 50 degree Kelvin superconductors, and some of them are up at 70 degrees, and you scale the size of the pinning sites, you're smaller than an electron. So now we have to put defects into the crystal that are smaller than electrons. How do you do that? You can't do that. It's impossible to do that. And we all knew that. And so I actually wrote an article around 1990. I was so tired of hearing all this bull about how superconductors were going to change the world. And I wrote an article that said, you know, there's more than just T sub C. Okay, there's also critical current. One of the things that people would have laughed at me when I was in the 1970s if I had published a paper and I measured the critical current with the magnetic field aligned in the same direction as the current. So it's J cross B is the force you're worried about, right? And if you want to make the force go to 0, all you have to do is have the J and the B in the same direction, right? And so you would never put your sample vertical in the axis of the magnetic field of the National Magnet Lab because there's no force trying to destroy the superconductivity. But if you ever build a magnet, it's going to be wound, and the field, the current's going to be going in the circumference, and the field is going to be going axially. They're perpendicular, which is the maximum force to destroy the critical current. And if I had gone to a superconductivity conference and presented a paper where I measured the critical current when the two were parallel rather than perpendicular, I would have been laughed out of the room. Okay? In 1990, I was reading papers in Science magazine where people were getting fantastic critical currents by measuring it this way. Anyone who knew anything about superconductivity or magnet design, we were laughing at it. It was ridiculous. You could never build a magnet. It's impossible, at least that's what Maxwell said, to have a magnetic field generated by a current that's in the same direction. They're perpendicular to each other. And so you don't measure a property that has no relevance, but that's what they were doing, and they were reporting it. And they were saying, I should win the Nobel Prize. I came up with this wonderful thing. Your wonderful thing was garbage, absolute trash. And so, part of the rest of the story, in 1995, I became department head. So I was asked to go give a little talk about materials, kind of representing the materials department, over in Kresge Little Theater. You've been over to Kresge, this little conference room down there. And I gave my talk on the promise of new materials and stuff. And afterwards, some guy gets up and asks me a question, because this is 5 or 6 years later. He said, so what do you think of high temperature superconductors? Well, I was not really the right person to ask, because you can tell I get a little exercised about high temperature superconductors. And it's not that I don't know anything about it. I did do my doctoral thesis in the area, okay? I said, well, and I told him this. They have high critical temperature, they have high critical field, but they have lousy critical current, and the people who are measuring it and telling you that they're getting 10 to the 8th amps per square centimeter are doing it with the field parallel, not perpendicular. Because if they measure it the other way, the critical field is not 10 to the 8th, it's 10 to the 1st. Okay? 7 orders of magnitude difference. You'll never build a high field magnet. I said they may be, my answer was, they may be important for detecting magnetic fields in what's called SQUID, superconducting quantum interference devices. The US Navy got very concerned in the late 80s that the Soviets would be able to put a squid in a satellite, and all of a sudden these big magnetic submarines would be magnetically visible in the whole ocean. They'd light up like a light bulb to a squid detector. At the time, you could even fly an aircraft at 10,000 feet above the ocean with a squid detector, and you could find the magnetic field signature of the steel submarines. The US Navy, ever since, they wanted to build a titanium submarine because it's non-ferromagnetic. They now want to build a stainless steel submarine because it's non-ferromagnetic. They want to get rid of this lousy ferromagnetic iron because superconductors can detect those submarines. And the question is, could they do it from 100 miles in the air? And with high temperature superconductors, it might have become possible. And in fact, I don't know, I haven't followed that part. But anyway, my answer was, so far as, because people were talking about magnetically levitated trains and all these wonderful things, and I said, well, you're not going to see magnetically levitated trains and big high field magnets in our lifetimes or our grandchildren's lifetimes. See, there's the sound bite, right? That someone will remember, right? Or we won't see it in our grandchildren's lifetimes. Well, it turns out a vice president of American Superconductor was in the audience. He was not happy. American Superconductor is a spin-off of this department, okay? From my point of view, the best thing, it was Greg Urich, John Vandersan, and Yet-Ming Chang came up with this way to internally oxidize silver and make the high-temperature superconducting ceramics. And so from my point of view, the best thing that happened about high-temperature superconductivity was I got Greg Urich's office, okay? Greg had come 6 months before me as a junior faculty member, and he had been given John Wolfe's old office, which is right there on the Great Court. You know, it's one of the nicest offices in the department. But he got that office. I didn't get it. When I was acting department head in '89, he came in and said, "Tom, I'm going to resign as my tenured position on the faculty." I said, "Why?" He says, "I'm going to become president of American Superconductor." I said, "Greg, you don't have to resign. You can take a leave of absence." "No, no, I want to do it the right way." And he did. To his credit, he took, you know, he resigned, gave up his tenure. He didn't have to. He could have held on to it for another 3 years if he wanted. And he went off and founded American Superconductor. And now 22, 23 years later, American Superconductor is kind of limping along. And if you read about them in the paper, the Chinese have stolen their wind turbine technology, software and stuff, and their stock's falling and stuff. And they put in some transmission lines in New York City. But we're not riding on magnetically levitated trains, are we? That was my prediction of 25 years ago. Now, it's not our grandchildren's lifetime, but my grandchildren have been born since then, okay? And we'll see if sometime in the next 50 years we will be riding on superconducting, magnetically levitated, high-temperature superconducting trains. I will bet we will not, okay? But when I said this, he went over to Mike Seema's office immediately. He complained to Mike Seema. I went back to my office. I was the department head. Mike Seema called me up and just reamed me out. "How could you say this? You're the department head. And, you know, I have research money with American Superconductor." I said, "Well, good. You know, I'm glad you do." I said, "I wouldn't take it." Okay. And he says, "How can you say it?" I said, "Mike, quit acting like an 8-year-old. I said, "I have an opinion. I have a right to my opinion." And he says, "You don't know anything." I said, "Mike, I did my doctoral thesis in there." So the next thing I know, about 3 weeks later, I get a call from the Dean of Engineering. "Tom, can you come and see me and meet with Mike Seema?" Okay. So Mike had gone to the Dean of Engineering, who was Bob Brown, who's now president of Boston University. We go over a couple of weeks later, we get all together. We're sitting in Bob Brown's office, and he says, "Tom, Mike says you told him to quit acting like an 8-year-old. I said, "That's right." And he says, "Why did you do that?" I said, "Well, if he'll quit acting like an 8-year-old, I will not call him, tell him that." Okay, so, and Bob Brown literally just, okay, the second time in my life someone's done that, just dropped their head in their hands in frustration. So, in any case, I have opinions. Back in the early 90s, I also had opinions about all aluminum automobiles. People were predicting that because of the price of gas and all this other stuff, that we were going to be riding around in 5 years, all the cars would be all aluminum vehicles. Because at the time, Audi was starting to come out with an all aluminum vehicle. And again, it's the same type of thing. The people they were talking all this great hype about the increase in the price of gas and how the aluminum vehicle was going to wipe out steel, and the steel mills were all going to fall apart, and you know, no one would invest in the steel industry. They're totally foolish to do so. And I used to say, we will not have all aluminum vehicles for another 20 years. And everybody was just shocked. How could I say this? Well, first of all, do you know how long it takes to design a new automobile? The new car that comes out tomorrow, when did they start that? 3 to 5 years before that, they started designing it. It takes 2 years to buy the dies and have them machined. for the stamping of the sheet metal, okay? And I used to tell people, anyone could build a $40,000 Audi, because that's what they cost back 20 years ago. Now they're about 80,000 or 100,000, right? But I said anybody could build a $40,000 vehicle out of aluminum. We built an all-aluminum Duesenberg in the 1930s. But no one's going to build a 500,000 vehicle per year Ford Taurus, because that was sort of that was the Toyota Camry of 1990. Okay, it was the largest selling vehicle in the country back then. No one's going to sell. In fact, Joel Clark had a student who went on to become an assistant professor at Harvard Business School, and her doctoral thesis was to compare the cost of an all-aluminum body in white with an all-steel body in white. A body in white is just the metal structure without any paint, without anything else on it, just the metal unibody construction. And in early 1990s dollars, the cost of a Ford Taurus was $15,000 to $20,000. And guess what the cost of the steel frame, the unibody frame, was? $500. Yeah, you remember what I said the other day, didn't you? Or did you know that? Actually, I said it about 2 or 3 lectures ago. But in any case, you're right. It was $500. And the all aluminum was about $1,000. Well, I could have predicted that, and I gave you a defense industry materials for the 21st century, my little 4 or 5 page thing on material selection, because the relative price of steel to aluminum is about 2 to 1. So, duh, okay. It's not hard to estimate these things, okay. And you say, well, gee, it's only $500 more. It's only $500 more to buy that car. The problem that she didn't recognize in her thesis, she assumed that you could resistant spot weld aluminum just like you do steel. Remember I said it takes 3,000 spot welds in the average automobile to make, because you need 2,000 good ones? I estimated the average, there are 50 billion spot welds made for automobile production in the world. Actually, maybe 100 billion now. If you build 30 billion cars, which is about what they build, and you got 3,000 spot welds, that's 90 billion spot welds, I think. Okay, 30. Did I do that right? Anyway, whatever the number is, maybe it's 1 trillion spot welds. But in any case, I had estimated that the spot welding in the average automobile was about a nickel per weld. So the nickel weld times 3,000, what's that, $600 for welding? I think that's right. So the welding cost was equal to the material cost. And if you go to that little handbook I gave you, or that little paper I gave you, the material cost of a car is about 10% of the cost of the car. And the welding cost, the joining cost, is about 10%. And the stamping and other costs may be 10%, because how much of the stamping of the metal you buy, what's the buy to fly ratio for sheet metal of an automobile? It's about 2 to 1. Half of it goes into scrap, because when you punch out those holes for the windows, that's scrap, right? Out of that sheet metal. So you start putting all this together. If anyone really looked at the details of how you fabricate something, sure, the metal for the body in white was $500, and it was $1,000 for the aluminum, but the as fabricated cost was not, the actual building the base vehicle might be $5,000 to $10,000, and it was another $10,000 if you made it out of aluminum, because of the increased cost of welding, the increased problems in painting, you know, everything else that goes with it is more difficult. Okay, so would people buy a $25,000 all aluminum Taurus as opposed to a $15,000 all aluminum Taurus? Well, go figure out the value of a pound saved. You'd save about 500 pounds or 300 pounds on the vehicle at $2 a pound. You could save $600 and spend $10,000. Which one? Do you think people will do that? Okay, figure out the economics. This is stuff you can do in your head, okay? But, you know, people, I'm sure I could go back in the 1990s and find articles where people are saying the steel industry is going to die, aluminum is going to grow, and blah, 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 okay? And anyone with the slightest conception of how the thing is fabricated and what the costs are knew that was ridiculous. Same thing about the high temperature superconductors, okay? But hey, you go read the Wall Street Journal and they'll have articles on there. People think I should be reading the Wall Street Journal. I say, the Wall Street Journal is old news. You know, by the time I read something in the Wall Street Journal, I don't want to invest in that because everybody else is going to invest in it. You need to get to something early. And people say, well, what are you going to invest in? Look, if I knew that, I'd be a rich man. I wouldn't be here teaching you, okay? I would be out doing something else. Anyway, this was not what I was going to lecture on at all today. But nonetheless, if we're talking about materials, there are some important lessons here. People join bandwagons, okay? And whether it's the government or whether it's Wall Street, people read these articles and they are not knowledgeable people. And they're the decision makers, okay? There's a guy, Kim Clark. Anybody know who Kim Clark is? Anyway, Kim Clark was dean of the Harvard Business School. Kim was a graduate student in labor economics at Harvard when I was a graduate student here at MIT. Our wives were sort of best friends, okay? His oldest son was born about 2 weeks apart from my oldest son when they were about 8 or 9 years old. I had them in Cub Scouts when I was a Cub Scout den mother. When Bryce Clark was about 10 years old, he knocked my son Matthew's 2 front teeth out twice in 6 weeks, okay? Bryce was sort of a bully and Matt was sort of a wuss. But anyway, actually, Matt we taught him you don't fight. And he came home when he was in about 4th grade. He was just in tears because he was being bullied and he wouldn't fight back. And we had taught him you don't fight. And he was just in tears. He didn't know what to do because we had taught him not to fight. And you know, when they were bullying him, I said, well, fight back, Matt. And he said, but you told me not to. And I thought, well, yeah, you're right. Okay, I told you not to. Anyway, so there are these conflicts that you run into in life. And Matt was running into conflict. Anyway, so when we're assistant professors, okay, he's at Harvard Business School and I'm at MIT. When I started out at MIT, I had a $50 first year budget, which we don't have to go through, but I got nothing from MIT. I used to say you get a desk, a local telephone, and the MIT name. And the only thing that's worth anything is the MIT reputation and the name. Kim, on the other hand, I was busy writing proposals. He was writing a proposal at Harvard Business School. He took it into the director of research, and he wanted to get $200,000, which would be like $1 million today, okay, for this proposal. And the director of research said to him, well, why are you writing this proposal? And Kim says, well, I need to get some money so I can hire some graduate students. He says, if you need some money, we'll give you that, okay. Well, I've never had a department head here at MIT say that he would give me $1 million. In fact, I've never had one tell me he would give me $1,000, okay? So there's a very different culture between the two schools. And of course, I've been in the steel industry and worked for them. And this was around 1980 or so, and we had our growing families. And Kim had taken his family down to Disney World. Well, I couldn't afford to go to Disney World. But he had gone down there because he was talking to the presidents of the American Iron and Steel Institute, okay? I'd never even met a president of one of the steel companies in the United States. But he was at Harvard Business School, so he was going down to talk to him. I said, well, Kim, what did you tell them? Because, I mean, Kim came over to help me build the Pinewood Derby track that I was building for the Cub Scouts. He was the only parent, to his credit, who I asked all the parents to come help, and Kim was the only one who came by. Unfortunately, Kim was not the most mechanically inclined person. I used to describe he didn't know which end of a screwdriver to use, okay? And of the 3 tracks, the one that he put in is the only one that kind of goes like this, okay? And so I knew which one not to race my kid's car on. But in any case, Kim was a nice guy. I said, what are you what are you talking? The reason he could take his family down there is because he was being paid this big honorarium to talk to the AISI presidents. I said, well, what are you telling him about steel? Because here's someone who really doesn't know a whole lot about steel, okay? And he says, well, I was telling him, how do you make decisions in the steel industry? I said, well, how do you make decisions? He says, well, for example, in the 1960s, Armco Steel was putting in a brand new steel melting facility, and they had to decide whether you do ingot casting or continuous casting. And I talked about yield, I think, before. And ingot casting was 65% yield, and continuous casting was 97% yield. This was the mid-60s. And continuous casting had been around for about 5 or 10 years in Europe. It's just kind of a new thing. And Armco decided to go with ingot casting. They were going to put in a new $200 million facility, and they decided to go with ingot casting. And I said, yeah. And I said, so you're telling me that was a bad decision? He said, oh no, that was a good decision. Well, it turns out 5 years later they had to rip it out and put in continuous casting. And anyone who knew anything about the steel industry would have known that. But the steel industry executives, who were all trained at places like Harvard Business Schools, were so risk averse. They were not going to put in any new technology that would have an immediate 50% improvement in productivity, okay, unless it was a proven technology. They were not going to be the market leader. They were going to be the market follower, okay? And that's what they were being taught by the likes of the faculty at Harvard Business School. Kim went on to become the dean of Harvard Business School. He was one of the great gurus in American automotive production. Even though if we walked through a plant, I'm not sure he could tell you what was going on in an automotive assembly plant, okay? But this is one of the wonderful things about an MIT education. We teach you exactly what you need to know about the technology, and then someone from somewhere else is going to run the business. And to give you a very specific example, one of my students from Taiwan, who did a great thesis in welding heat flow, Nansen Chai, went on to, he and one other guy from Stanford were the two right-hand people of Morris Chang. Anybody know who Morris Chang is? I think he's still alive. He founded Taiwan Semiconductor Manufacturing. They are the merchant foundry that grows 80% of all the silicon in the world. And they are now a multi-billion-dollar company. So Morris Chang had been at AT&T Bell Labs, and he got some money out of some venture capitalists in Taiwan, and they decided around late 1980s to start this worldwide, merchant foundry for growing silicon. So Intel, Motorola, anybody you can think of, the Taiwanese were growing silicon cheaper than anybody else, and so they just took over most of the world market for growing the silicon single crystals, and became very, very wealthy. And so in the mid to late 90s, when Morris Chang stepped down, it was really between my student Nansen and this other student who had studied material science and business at Stanford. Guess who became the head of Taiwan Semiconductor? The student who had studied business. And Nansen, my student, who back in the 1980s, I was teaching my students what wonderful things science and technology was. And I had instilled in him this attitude that science will win the day, right? And he's now in charge of their big venture capital fund. He's sort of an executive VP or something, and he's very comfortable. He's made a lot of money, but he's not running the business. Because what does MIT instill in you? We teach you how to be some of the best technicians in the world. We don't teach you to be the leaders of the world. We teach you to be the technicians to the leaders. Isn't that great? And I've been arguing this with the faculty around here for 20 to 25 years, and they don't understand what my problem is. We teach you how to solve differential equations and all kinds of things, and you're the best in the world at it. And some of you will become the leaders, but most of you will be the people working for the leaders, because the leaders will be the people at Harvard Business School who know all about, you know, making good decisions in the steel industry, or reading the Wall Street Journal and knowing where to invest their money in materials. So this may not have been on deformation processing, but hopefully it will get you thinking about some things that may be more important to your career than how to stamp sheet metal. Okay?